All right, here we are on, almost said video. Well, it's kind of a video. Tape, I almost said. Wow, dinosaur. Well, here we are on the recording, talking about non-renewable resources. And as I was staring at the subject of this chapters, 2 chapters actually, I was thinking, they changed the title. Because the idea of something being non-renewable isn't all that useful. I mean, yes, we can think about things that are obviously limited in quantity, but those limits, those physical limitations, are not really all that meaningful. Well, let me just briefly explain before we get into a discussion of the things that are called non-renewable resources. So first of all, the definition. A non-renewable resource is something that's exhaustible, used up, if the quantity cannot be significantly increased during a time frame relevant to people. That's certainly true for things like coal and oil and gold and silver. But the reason that this notion of its physical finiteness is not all that helpful is because some of the physical amount is so scattered and so inaccessible that the issue is really the cost of extraction changing as we use what Mother Nature has granted to us, more than just the fact that there's not any of it left in the ground or in the water or wherever left to take out. And another reason that that's sometimes not all that useful a concept, I say sometimes, because if we think about something like silver or gold, well, sure, that's a non-renewable resource, but when we use it, when we've taken it out the ground and make it into something that's useful to people, unless we left it out in outer space someplace, it didn't go anywhere. We just moved it. We moved it from under the earth and did stuff to it, and now it's somewhere else, but we still have it. So then again, the issue is cost, not physical availability. Now, I said some because oil you burn and natural gas you burn, so you can't recycle that. So the issue in terms of non-renewableness is more economic in terms of ability to recycle and cost to recycle, which means to gather it up after it's been scattered by use by humans, or to still look in the ground to see where some of it is. And so what's typically going on is they were trying to figure out ways to find natural resources that can be taken out of the ground or wherever they occur naturally for a lower extraction cost than what we can sell them for after we spend to make them available in ways useful to human beings. Okay? So that brings us to our first critical concept that's part of discussions that are sometimes really bizarre among lay people for non-renewable resources for reasons that I've gotten into a little bit already. But the first critical concept is the concept of current reserves. Okay, so these are known deposits. We found them, we've mapped them, we've scoped them out, and so we know where they are, and we've determined, based on our technologies and current prices of things that it takes to do their extracting, that these quantities, these known deposits, are profitably extractable after we take them out of the ground and turn them into something useful to humans. At current market prices, we can sell them for enough to cover our expenses at least, and if we're lucky, maybe for more. Like, whoopee, a gusher, we're rich. Now that means that it's going to be cheap to process the oil, and maybe the current price is high, and so, wow, you're going to be able to sell it for a lot more than it costs to get it to a market. Okay. Known deposits, profitably extractable. That's really limited, and it's just patently obvious that that's only a fraction of what we have out there. Yet a lot of people make a big deal about what's called the static reserve index, another sort of a critical concept, at least to understand its likely misuses and its few reasonable uses. Static reserve index, SRI for short, in case you see the alphabet soup, you'll know what it stands for. It's the result, that number, the static reserve index, is the result of taking right now the current estimate of known deposits that are profitably extractable, current reserves, and dividing it by the amount that's been currently consumed, taken out of the ground for human use. And then, incredibly, I guess reporters are out there looking for a good story, and you know, if it bleeds, it leads, or if it scares, you know, it's going to sell newspapers and get people to go to websites. And so they go out there and shop around on the internet and find some SRIs, some static reserve indexes, for some things that look frighteningly small. You know, divide the current reserves by current consumption for some things, you know, 10 or 15 years. We're going to run out of, you know, whatever in 10 or 15 years. I remember being in graduate school in 1980s. Sorry, I hope I don't look as old as that says that I am. And there was a report, an article in the U.S. News and World Report. This is, that magazine may have been gone. It was around until a few years ago. It was a major news magazine when it was around for most of its existence, U.S. News and World Report. And an article that made it past the editor, well, by the author first, and then past the editor of the U.S. News and World Report, said that Texas was going to run out of oil in a few years. And never mind how meaningless that is, or whether some particular place, I mean, at least for the United States as a whole, maybe not so meaningless to Texas, that Texas was going to run out of oil by, you know, before the year 2000, within a few years. Whoa, well, you know, here we are, and this was recorded in July 2016, and we're not anywhere near out of oil in Texas. Till the price sank recently, it was just booming like crazy, and even at the current lower prices that we've had recently, there's still plenty of oil being taken out of Texas, and we know there's a lot more down there that's profitably extractable if we further improve our technologies, or if the price should happen to rebound and go back to where it was just a few short years ago. So some knucklehead, and there's been these, he or she, I think it was a he, is not alone, thought the SRI, being a small number, was we were going to run out in that many years. He didn't understand, among other things, that if we started to get close to running out, that maybe the price would go up. And that would do two things, namely cause a frenzied search for more, which is what happened when the price went up about 10 years ago a lot. You drive down US 287 in West Texas, there were signs everywhere of exploration for oil. There were lines across the freeway, not the freeway, just the regular highway, that showed that they were setting off explosions all around to try to generate seismic waves to try to judge where there were deposits of oil. And, well, since the prices dropped, the activities slacked off a little bit. But there's still plenty of oil in Texas and every place else. And all the oil fields we've ever tapped into, even if we've gone back to them via fracking, have more oil in them still than have ever been taken out. And so we get ourselves in trouble if we don't understand what current reserves means and what the limitations of it are, and how quickly it can change from changes in price and changes in discoveries and changes in technology. Now, how might the static reserve index be of some use? Well, it might signal to us that when lacking discovery, prices are likely to go up. So if you're an investor or somebody in business that uses one of these natural resources, if the SRI is starting to on a downward trend and it's getting to be a not too large number, you might want to start looking for substitutes, not because it's physically going to run out, but because maybe the next available resource or discovery that somebody makes is going to be for something that's a potential reserve, not profitably extractable at current prices, but maybe at future prices or with future technologies. And maybe the MEC sub, I'm assuming you read your chapter, the marginal extraction cost for a substitute, is starting to look like a more attractive way to operate your business than the so-called non-renewable resource that you had been used to using. All right, so I've already touched on the next critical concept, potential reserves. And these are everywhere. It's, you know, that's why the fracking boom was such a big deal, in talking about oil, because we knew where there was a lot of oil left that until the fracking technology came along was not profitably extractable. Okay, so that's what potential reserves are. We know where there's stuff, oil, coal, silver, gold. And heck, a mile of seawater has all kinds of stuff in it, lots of it. But most of it is not, unless it's salt, it's not profitably extractable yet. Someday, who knows? All right, so potential reserves are known deposits that are not yet, and may never be, profitable, extractable. And they can immediately become current reserves if prices were to change or if technologies were to improve. But they may never become, depending on how unprofitably extractable they are, even with, we may discover, for example, that there's all this gold and silver in seawater. And so we may somehow call that a potential reserve based on the fact that we've tested seawater for all these trace elements. And we said, well, there's a lot of seawater. But no, not profitably extractable any time soon that I know of. You never know when some genius is going to invent something. Okay, and so then the third critical concept in this list of things, and I've mentioned more than 3 already, so let me just back up. And by the 3 critical concept, I mean current reserves, potential reserves, and now the third one, the resource endowment. Talking again about the seawater and everything in it. I mean, there's our resource endowment. 4/5 or 3/4 of the earth is covered by water, and everything that's existed on land is diluted or dissolved in seawater. And so we have a huge resource endowment of things. We are not going to physically run out of even the things that we can't recycle because some of it is just out there in such minute quantities per unit of water or soil or rock that it's not likely we're ever going to extract it, at least in our lifetimes. And so, well, there it is. And some of it, we just haven't found it yet. And we can infer that it's out there from past rates of discovery and, how often we find things when we look in certain ways. And so we can infer that reasonably infer that the resource endowment for most things is vastly more than the potential reserves or current reserves, and a lot of that is capable of being at least potential reserves in the sense that it may be close to profitably extractable, or even a current reserve once we find out exactly where it is. Okay, so those are the big 3 things to keep in mind and to judge the frequent scare tactics that you hear about in terms of something about to run out. We're not going to physically run out, but we better keep looking and inventing because we're either going to have to make some substitutions or figure out a way to get things more cheaply, or a lot of things are going to become more expensive and lower our standard of living, and we don't want to do that. All right, now backing up into the course a little bit, now we're going to look at natural resources as if they're commodities. Okay? And we know that they can serve as other things. A wilderness area is maybe more valuable left alone. No cut trees except maybe a few to put in a trail, and no mining, no grazing. Just leave it in close to natural as we can in a way that humans can still enjoy more than the edges of it. And so we're going to say we're past that point. We've decided no, we're not. We've opted for extracting the natural resources to put them into manufacturing processes for human use. And then that raises the issue of, given the uncertainty about future supplies and costs and the ability to recycle and all of that, and the demand and changes in demand over time, if we opt for extraction, decide that it's better to serve our desires in a manufacturing process rather than its nearly natural state, how much should we expect to extract? How much should we plan to extract? And at what rate should we do that? And we recognize quickly that we're going to have to make choices with limited information, and we're going to have to make the choices in a way that we can adjust them reasonably for when we learn more. So, for example, next year we may decide that the choice we made this year in terms of how much we could extract now and then how much to save for later that we've already found is not the right choice, and we should either go slower or faster. But we've got to start somewhere with the information that we have. And so we have to first recognize, okay, so what general concept defines the optimal rate? And so I don't have to speak alphabet soup. I can tell you that, well, we know the optimal rate for everything, most things, some exceptions, I suppose. It's always scary to use the word always or never. But in your microeconomics price theory, the gains from trade are maximized when the quantity is such that the marginal cost is equal to the price. So that's still true, except now, since we're dealing with something that is usable, is non-renewable in some sense, to where we take some out of the ground, there's less of it in the ground than previously. The price equals marginal cost becomes a little more complicated. Again, so I don't have to speak the alphabet soup. I'm holding it up. That saves me having to write it down here. And yes, I am going to use the easel here with something that's on it eventually, but not till towards the end. And that's one of the main reasons to record this rather than have this be one of my regular lectures, is because then you can go back to this graph on here. I'll say it a couple times. Once now, you will see a version of this on your exam. Okay? So the question is then, will you understand what it says then? We'll go over it a couple times. Once today on the video, and then it'll be recorded for you to be able to look at again, and we'll do it again in class, fishing for questions. But anyway, so the quantity that maximizes value to society is such that, given current technologies and current knowledge about future availability of the resource, that the marginal extraction plus the marginal user cost, using now, having less for later, sums up to the competitive market price. All right. So, as I said, the marginal user cost depends currently on the expected future value of the resource, right? So if we think it's going to be worth a lot more later, then that says, well, don't use so much now, use more of it later. So we could rewrite that equation, definition, statement of a condition a little bit differently to take into account that factor. The price in time period 1, which would be next time period, is equal to the current time period 0, marginal user cost, times 1 plus R. That's not a funny looking V, that's an R. That's the discount rate, our rate of time preference. And I say our because it's going to be the rate of time preference of who's ever at the mine or the forest or wherever it is we're doing the extracting. It's going to be their rate of time preference. And that's not necessarily the optimal rate of time preference, because maybe the social rate of time preference, the optimal rate from society's perspective, might be different from individual owners of pieces of the resource, their time perspective. That's a key issue to address, at least mentioning it in our case, and for others that get more deeply in this, to research its basis and what to do about the fact that uncertainty and regulation and other things that affect people within the range of their lifetime makes them maybe do things faster than would be optimal from society's perspective with a presumably longer time horizon than just one person's lifetime. Okay, so MUC1 is equal to MUC0 times 1 plus R. And so, anyway, the marginal user cost would go up over time by the rate R, whatever it happens to be. You can sort of think about it like an interest rate, right? We prefer money today to the exactly same next year, all else equal. So then we're asked, well, okay, if you'd rather have $100 now rather than $100 next year, how about $105 next year instead of $105 now? And now you're thinking, you know what, I'd rather have the $100 now versus what $105 is likely to buy next year. And so now it's not so sure. Depending on your rate of time preference, maybe you'd rather have it now than a little bit more later. That's why some people save more money than others do from their current paychecks. All right. So all of this ends. By all of this, I mean all of this gradual change in price and user cost over time, assuming no disruptions from the way we think things are likely to be and the way things are based on current technologies and abilities. All of this ends with the price reaching either the choke price, okay, P max it's sometimes called, or the price equaling or rising up to the level of the marginal extraction cost. And we get back into class, and we'll go through some specific number examples. Those are not as amenable to going over in a video. So I'm not going to attempt to record a lesson on that because that'll involve a lot of going back and forth and writing equations. It might be hard to see. We'll save that for later. Now we're just going over the broad outlines that we'll get into there, and maybe warning some of you that maybe you better read that part of the chapter really closely, or it'll all just go over your head when we get into it in class. Again, please be a prepared student. Okay, so what do we mean when we say this all ends with the choke price or the marginal cost of the substitute? Well, that just says, as an example, if the price of coal gradually increases as it seems to be becoming more scarce because someone hasn't found more of it, or when they find more of it, it's gotten more expensive to take out of the ground, all of that ends when somebody finds a substitute for coal that does the same thing for a lower per unit cost, the marginal extraction cost for some substitute. And thinking in terms of energy, the ultimate marginal extraction cost, the ultimate limit on how high the price for anything can go, is the cost of capturing solar energy just in raw form. Photovoltaic, it is. It's darn expensive now, but the cost of it is coming down. Ultimately, that says that any resource that we have in the ground, a non-renewable resource, that costs more to extract than capturing sunlight, that's going to stay in the ground, right, until somebody invents some technology that makes it cheaper than sunlight. Okay, so that's what we mean by MEC sub, marginal extraction cost of a substitute. That sets a limit on how high the price of a non-renewable resource can go, and sometimes the MEC sub that's relevant in the short term for a non-renewable resource is just the extraction cost for another non-renewable resource. So, the price of something goes up over time because it's getting more and more scarce, and then it hits a limit at which we stop using it and switch to something else because it's cheaper to use for some valued purpose now than the other stuff was. And then there's that choke price. Most natural resources are not desired for their own sake. Some, gold, silver, we like them because they're shiny. And, we use some gold like in teeth for other uses. And then, that becomes relevant if we have some other way to make crowns for teeth in some way that's more durable and performs better than gold does at a lesser cost, fine. There are most things, including like that use of gold for use in teeth crowns. The relevant substitute is some other non-renewable resource. Okay, so if we hit, for some things, we'll hit what's called a choke price before we'll hit an MEC sub, and that means we hit a price for the end use of the resource at which people no longer want that end use. And they switch to some substitute for that end use. That sometimes happens or can happen. So those two things, either the limit on how high you can show, how high the price can go for some end uses of the resource, or just the ability to switch to some substitute will define how high the price can rise in the absence of likely disruptions in that price trend over time because of discoveries and changes in uncertainties which affect that R in that equation, the R that sort of looks like a V, right, in this equation, marginal rate of time preference. For those of you wondering why I'm not always looking into the camera, first of all, I have to look up. And being 6'6" inches tall, I'm not used to looking up, maybe straight at students, down a little bit because they're seated, but occasionally I have to look at my script. So anyway, pardon me for not looking at you directly all the time, but I do have to keep up with my script here and make sure I don't accidentally go off on a tangent and skip something. Okay, so that marginal user cost at times will shrink. Why would it shrink? Well, because if the accessibility of the resource is going down, it's less and less valuable to have the resource than if the quality or accessibility of it remains constant. You'll see that in my graph here that I'll reveal shortly. My cover sheet didn't quite cover all of it. By the way, you'll see from what little you can see of the graph, I should mention this 2 times. You see some of my scribble here? I am so used to putting Q on the x-axis of my graphs that I started to do that before I said, oops, this is not a graph in which we're graphing quantity against something. The issue here on the x-axis is time. So these are all little t's. Okay. All right, we'll see the rest of the graph in a minute, but don't you do the same thing and sketch the graph real quick and put a Q there. Put a big T there, time, and or a little t, or the word time. Okay, so there are several reasons that the time trend, which is what the graph is going to show, for a natural resource could be pretty jagged, and the history is for most natural resources, the prices go up and down because there's all kinds of things going on. In the immediate term, there is shrinkage in the abundance of what we have. There's that SRI concept. We're using some of it up. We're extracting it from the ground and making it less extractable by recycling, by using it, and so it's scattered in landfills all over the earth. Or if we're talking oil or coal, we burned it up, and so it's the possibility of recycling. Use of it permanently reduces the amount available in a time frame relevant to people. So what time frame relevant to people? What does that mean? Oil and coal is being made by Mother Nature all the time, but not fast enough to matter over even a couple 100-year society span for countries typically, much less humans living 80 to 100 years old typically. Okay, so other things that could affect the price trend is, as I said, the marginal extraction cost. That's kind of the floor from which prices rise with marginal user cost going up over time. Marginal extraction cost could drop. Typically, it doesn't rise unless we get into lesser and less accessible stuff. Then it can. So the marginal extraction cost at times can take up, as for example it has with the fracking. The technology can suddenly make it cheaper to do exactly the same thing, like suck oil out of the ground, or natural gas, or coal. Okay, so let's kind of jump right into this graph, and when we finish with that, that'll conclude this. And I'm going to walk off the screen here for just a second, but don't. I'm not accidentally going to. It's not going to be that I'm going to accidentally forget to turn the video off. My throat's kind of dry, and I'm going to lubricate it a little bit. In the meantime, while I'm off the screen, I want you to take a look at this graph and see if you can figure from what you've just heard and reading your chapter what's going on, what happened up to T1, between T1 and T2, and so on, and what's probably or very likely happened at those time points in time. And then big T is typically the time at which we switch to a substitute or stop extracting because we're up to the choke price. So that means up here at this level, let's see if we let's just say it's the MEC sub. Okay, so that's where we get up to that point. It's like, okay, we're up to the marginal extraction cost of the substitute. So that's when we make the switch. Okay, so off the screen for just a moment while you stare at this graph and try to figure out why the price suddenly does what it does and the marginal extraction cost does what it does. All right, I wet my whistle a little bit. I'm back. Hopefully you didn't tune out and try to do something else while there was silence and nothing on the screen but my easel here. Because sometimes we learn more and we retain more when we try and fail first, hopefully at a low cost. And if we just go, ooh-de-doo-de-doo, he'll tell me and I will write it down and I will memorize it the night before the test. And then forget it totally after that because I never understood it to begin with. Yes, I'm lapsing into some sarcasm because I've been doing this a long time and I'm so doggone frustrated by that because, as you know from the first video, one of my guiding principles is to try to make a difference. And if all you're doing at the other end of this, the classroom or the other end of this video screen, is memorizing this and trying to remember it long enough to answer a test question, I'm not making a difference. And you're not getting much for the money you're spending on this. So All right, let's try to intuit this. Up to now, up to price T1, well, not now, but up to, from the initial, from the start of our time frame here, up to time period or time point T1, marginal extraction cost was constant. And the price was rising gradually. And then it took a little hit there and went down and then started going up gradually again. So what's going on there? Well, the marginal extraction cost is constant, so accessibility is constant. So we're depleting some of what we have in the ground, so the marginal user cost is going to go up. So price goes up because the MUC part of MUC plus MEC, there I go lapsing into alphabet soup again. The MUC part of MUC plus MEC is going up. So the price is going up, even the marginal extraction cost is going down, and then it goes down, and then it keeps doing the same thing for a little longer. What probably happened here at T1? Teacher, I know. Well, sorry, I can't see your hand telling me. Since I'm an optimist, I'm imagining you out there in the video land. Well, duh, prof. What happened? The only possible explanation, among at least the ones we've discussed, that are relatively general and simple, is a decrease in demand. Yeah, that's what you thought, right? Right? I mean, the demand decrease means the price is going to go down, despite the fact that we have less in the ground than we had before, and the fact that the extraction cost hasn't changed at all. Okay, and so then after the demand decrease, well, then we do the same old thing for a while longer, because, yeah, we're depleting more of it, so the marginal user cost is going up, and the MEC is staying constant, so, yeah, the price is increasing. And then we hit time period T2, and whammo, the price goes down big time. And now we look and see that the marginal extraction cost went down by about the same amount. I meant it to be an equal amount. So what happened there? A technology improvement, lowering the extraction cost, decreased the price by about the same amount. Okay, again, we're assuming competitive market, so that the price is going to equal the marginal extraction cost plus the marginal user cost. So, okay, so T1, a decrease in demand. T2, a decrease in the extraction cost because of improved technologies. Okay, so then what's going on from T1, T2 to T3? Well, it looks like maybe a slightly lesser increase. It's probably indiscernible, but if I could fine-tune my graph so that there would be a lesser increase in the rate than it had been previously, certainly less than here. Maybe it's not obvious, less than there. What's going on there? Well, that means the little r. The little r. Does that look like an r that I just did in air? Okay, the little r, the rate of time preference, which may vary between individuals running mines or timber cutting operations or oil wells, which may differ between them and society as a whole. That went down a little bit because of uncertainties. That maybe discoveries were going to be easier to do. The extraction cost wasn't going to be, maybe the cost of exploring was lower. Those would be the kinds of things that would reduce the rate at which the user cost would rise with the depletion of the resource holding MEC constant. Now we see at T3 a jump in price. That's the counterpoint here. An increase in demand, right? Nothing going on in terms of cost to extract, and the nothing going on in terms of the rate of increase over time when things are kind of settled, but a jump in price, an increase in demand. Okay, now we see at T3 what's going on. The price is still going up at the same rate, that the extraction cost is now rising. We no longer have a constantly resource with constant accessibility, constant marginal cost to mine it or to extract it, depending on if it's not something that you mine. And so here, with these lines squeezing closer together, the marginal user cost is getting smaller because what we're using is of lesser and lesser quality over time. That's a little harder to grasp. Some of the equations in the chapter will hopefully nail that down a little bit better. So read that with this clarification need in mind. And after you do that, and there's probably still going to be some clarification needs for some of you, let's make sure we go online and post those, and or I strongly prefer and. because I come to class better prepared if I can anticipate some of the questions. And or any clarification need here, go to your discussion forum and post those, and then we'll have plenty of discussion time left in class, especially if you do that for the things that we can't resolve in writing in the discussion forum. All righty, as I said the first time I showed you the bottom half of this, something like this will be on the test, so make sure you look at it really closely. I'll run through another one in a face-to-face interactive forum, and then there'll be another one on your homework, and then there'll be another one on the test. And so you should be able to figure out all the good reasons why you would expect price volatility in semi-non-renewable resources markets. And I say semi because that's really the only kind that there is. Thank you very much. The quantity cannot be significantly increased during a time frame relevant to people. That's certainly true for things like coal and oil and gold and silver. But the reason that this notion of its physical finiteness is not all that helpful is because some of the physical amount is so scattered and so inaccessible that the issue is really the cost of extraction changing as we use what Mother Nature has granted to us, more than just the fact that there's not any of it left in the ground or in the water or wherever left to take out. And another reason that that's sometimes not all that useful a concept, I say sometimes, because if we think about something like silver or gold, well, sure, that's a non-renewable resource, but when we use it, when we've taken it out the ground and make it into something that's useful to people, unless we left it out in outer space someplace, it didn't go anywhere. We just moved it. We moved it from under the earth and did stuff to it, and now it's somewhere else, but we still have it. So then again, the issue is cost, not physical availability. Now, I said some because oil you burn and natural gas you burn, so you can't recycle that. So the issue in terms of non-renewableness is more economic in terms of ability to recycle and cost to recycle, which means to gather it up after it's been scattered by use by humans, or to still look in the ground to see where some of it is. And so what's typically going on is they were trying to figure out ways to find natural resources that can be taken out of the ground or wherever they occur naturally for a lower extraction cost than what we can sell them for after we spend to make them available in ways useful to human beings. Okay? So that brings us to our first critical concept that's part of discussions that are sometimes really bizarre among lay people for non-renewable resources for reasons that I've gotten into a little bit already. But the first critical concept is the concept of current reserves. Okay, so these are known deposits. We found them, we've mapped them, we've scoped them out, and so we know where they are, and we've determined, based on our technologies and current prices of things that it takes to do their extracting, that these quantities, these known deposits, are profitably extractable after we take them out of the ground and turn them into something. All right, here we are on, I almost said video. Well, that's kind of a video. Tape, I almost said. Wow, dinosaur. Well, here we are on the recording, talking about non-renewable resources. And as I was staring at the subject of this chapters, 2 chapters actually, I was thinking, they changed the title. Because the idea of something being non-renewable isn't all that useful. I mean, yes, we can think about things that are obviously limited in quantity, but those limits, those physical limitations, are not really all that meaningful. Well, let me just briefly explain before we get into a discussion of the things that are called non-renewable resources. So first of all, the definition. A non-renewable resource is something that's exhaustible, used up, if useful to humans. At current market prices, we can sell them for enough to cover our expenses at least, and if we're lucky, maybe for more. Like, whoopee, a gusher, we're rich. Now that means that it's going to be cheap to process the oil and maybe the current price is high, and so, wow, you're going to be able to sell it for a lot more than it costs to get it to a market. Okay. Known deposits profitably extractable. That's really limited, and it's just patently obvious that that's only a fraction of what we have out there. Yet a lot of people make a big deal about what's called the static reserve index, another sort of a critical concept, at least to understand its likely misuses and its few reasonable uses. Static reserve index, SRI for short, in case you see the alphabet soup, you'll know what it stands for.